Okay, my friends, spectacular day today. If you know anyone that wants to get into physics or is a physicist, I recommend you discuss this with them. We're talking about neutrinos. It's official. Today it's official. For the first time, neutrinos have been detected in a collider experiment. Well, and this just came out. Now, what is a neutrino and why is this such a big deal, and why do I claim I knew about this long ago? This book or this paper was written in 2019. It's not exactly correct anymore. I need to update it, but it was on academia.edu back then, which is dipole electron flood theory, which means all particles are dipoles. Neutrinos have a dark and a white side. I'll show you that right now. Now, this goes back to when I was in the Army, and I was in nuclear missiles and that sort of stuff. And the transfer of energy is from light to atomic vapor. And that's all that exists is light. Light just adds up bigger and bigger and bigger. When it's all separated out and the little particles go flying through the air, it's light. When it adds together, I believe now the number is about 1,823 particles together, it becomes stable and becomes what we call a proton. Now, two particles together are not stable. That literally is electricity. But if you took two and then put two more with it, it becomes the smallest stable particle there is, which is called a photon. Let's talk about this. All right, I just want you to know something. I did this as deep as anybody. Now, this was a paper I wrote on about dipole moments and polar molecules and how crystals form and where the centers of positive and negativity are in these dipoles, and where the dipole moments are of different types of polar and non-polar particles, you know, magnetic and non-magnetic. And I went through this as deep as you could get through it. And I had electrostatic and nature, Coulombic forces, repulsive force between nuclei, repulsive force between electrons, attractive force between the nucleus. It's all got to do with dipoles. It's 100% dipoles. And again, that goes way back, as you can see. And I'm into this. I've been doing this regularly, so I'm not unknown to this realm. And I did take particle physics at University of Geneva. And I interacted with the professors and I showed them all my stuff. And they, I think, were quite impressed, because just shortly thereafter, they made some changes at CERN. I'm not kidding you. That's just a fact. They put in focusing magnets and they put in CMOS, because they said, oh, you can't possibly see these particles. I said, yes, absolutely. Here they are right here. Fermilab sees them somehow. I don't know how they saw them, but here they are in light particles. These are photons. All right, so these particles we can see, and we can see the dark matter, which is here. That's the dark matter, and that is dark matter. It carries the white matter. It pushes it, or it pulls it, one or the other. It depends on, you know, there's all kinds of different dipole moments. There's heat, there's light, which is basically the same thing, only one's a lot slower, and they even sound. And then there's chemical bonding that change, you know, there's interaction, bang, and mechanical, let's call it. And then there's chemistry that adheres to each other due to bonding. So let's just go with those two, make it a little simpler. Now, can we split apart these particles? Yes, we did it right here. The white separated from the black, and that is called precisely what they're looking for in all of these experiments. It's called electron neutrinos, which create the showers. Here they are right here. And the black particle separated away, and it just stayed the black particle. That's exactly what they say happens. No difference whatsoever. When they come through as light, they are two Dirac neutrinos back to back, just like two-bar magnets. That's why they're stable. If there was only one of them, that's not a stable particle. That's going to adhere to something somewhere. They're not stable until they reach certain zones, and that has like a ring around it of magnetism that says, I don't want any more and I'm not going to give any up unless you really be very, very aggressive with me. And then they can knock these parts apart and just splatter them all over, which is what we did because of that Venturi. Venturi's the key. And the black particles are like bombs. They're just bam, 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 and they squirt that white, which can get big and can get small. You see it? It's small, big here, and small there. It's only big there because it's pushing through these particles right here that are out in front of it, which are other molecules in the air, which is gases and so forth. They get excited because this has to get excited because it's pushing them out of the way. So, and this is Fermilab's pictures, and I have some other stuff from, well, here, hold on. All right, so this is Fermilab, and I followed them forever, and I was really disappointed because they won't talk to me. And they always ask, please send us any questions you have, and I did, and they just said, that's it, don't ever contact us again. These are the two particles, yes, black and white, no question whatsoever, I just showed them to you. Only they go this way because they're polarized towards the Earth, and they spin this way with a black and a white up and down, and they wobble. Now, in the between phases, the Majorna neutrinos are as they're building energies. And I can show you all of this stuff. Now, that's just the neutrinos they're talking about. This goes way back to 2012. And again, I started to try to interact with them a few years later. But anyway, okay, I showed you the particles, and they are just like this. And this one here can get big and get small, and that one never changes. It stays the same size always. This one can get very big or very small, and that's why it squirts through the Venturi. And these are the point-like particles, but these are, that right there is a muon, and that's an electron neutrino, as I showed you a minute ago. All right, you see this right here? When they're coming in this way, they're always attached together. They will not separate. Very, very hard to make them detach from each other. But in the Venturi, when it hit here with the black and the whites attached together, called the muon neutrino attached to the electron neutrino, the Dirac, it hit here and the white ones turned into a spray because they collide with every other white particle that has a field, and they're everywhere. This just goes on its own. It doesn't have any real field other than it pushes the white stuff out of the way. And I can prove that because I can show you a black wave pushing the white. In this particular Venturi setup, there was no black getting through at all. The black came back together over here. I don't know where it comes from. It's just, it's ubiquitous. I think it's just tons of extra stuff. I never realized you could break apart these white and black so easily. But there has to be a lot of extra black matter, and it doesn't interact, it doesn't have a field, it's not magnetic, it's none of that stuff. The white seems to seek it out, that's all I can tell you. But the black, as they say, it's dark matter. You can't see it, it doesn't react, it doesn't emit, it doesn't reflect, it doesn't absorb, and that's what you got. So once they split, you end up with the white showers and just the black balls. And those black balls never get bigger or smaller. See them, the same ones over here, just like here. And they add back immediately because they want somehow to attach. Now, I don't know which one of them pulls or sucks. One is the other. It's either sucking them together or one of them has to be attracting the other. Now, is it the black attracting the white, or is it the white attracting the black? Or is it some mutual agreement? I don't know. All right, so they're saying this is the first time it's ever been seen. I've been showing this since about 2015, maybe 2016 at the absolute latest. And it may even be 2014. It was right around that area. Because Rod Warren started posting pictures showing kind of crazy looking things like this. And I realized right away it was light, and he was separating the light. He's using a laser into a Venturi. And this is extreme luminosity, and that is the signature of increased energy. So I don't see why we can't get free energy by using this Venturi, which is totally passive, requires no extra energy whatsoever. All right, if I'm right about my claims, and I'm pretty darn sure I am, we should be able to send this light through this Venturi and separate the white, which is, that's the only thing you use to charge up a battery. That's the only thing you want is the white, but you got to separate it from the black. That's where it creates, you know, like a generator. It takes a lot of energy to run it. This takes nothing. The light goes through a crusher. So we're not hitting head on, but we don't have to. We're hitting sideways, and you can't get back out. The black keeps pushing it and pushing it and pushing it through here, so it squirts out. And you just squirt that white down into what they call a photodiode, so it goes down the photons of light, which is nothing more than the electricity, goes down through that diode, and the gate slams it back. Once it goes through, it can't get back. So it's being pulsed. And depending upon the number of pulses and the intensity of the laser, you should create all kinds of voltages. You should be able to create very high voltages. I think. Again, this is going to take some engineering. I don't have the capability to do this, but I do understand very clearly how easily this should be able to work. And right here, from the same people that I'm trying to get to look at my stuff, here's the electron showers, and they come through and they get huge. They're big white showers, yes. And here's the muon showers. They come through and they stop. They can't go any further. Now this is from, I forget who this is from, but it's one of the big accelerator places. Now I say if we can put this inside of here, this could be micro, this could be the size of a pinhead almost. And the Venturi is just a Venturi, it's just a restriction. Now, I'm not sure what kind of material you'd make it from, whether it be ceramic or some kind of metal, or I don't know. Because all this was done with was literally, and I'm not kidding, I know it sounds insane, but it was 2 finishing nails. And because they were nails, they have a rounded surface. All right, so when you shine the light, it had to go around that surface into the pinch between. He was trying to do a slit experiment. And instead of using a flat plate, he used these rounded things. And when it crushed into that rounded spot, it became a Venturi. And the blacks just kept slapping it through, and the white kept squirting through the other side. There was no other way for it to do. And then they came out in blistering white, which is extreme luminosity. See, they're upgrading CERN to do all the things that I did already. New technologies for high luminosity. They want to see these things glow like crazy. And yes, high luminosity expected to be operational 2029. I'm showing you luminosity, you can't get any higher. And this goes back many, many years. Molecular polarities, dipole moments, polar molecules, transfer of energy is from light to atomic vapor. And that's what I show very clearly. Now, how this all started was seeing these actual pictures of photons, and it just blew me away. And the reason was because of CMOS. All right, CMOS is a type of metal oxide silicates, and these things can pick up different vibrations of light. Okay, let's call them vibrations of light. They're different. In other words, like this. All right, one type of transition metal could pick up this, and it would bounce it back. Another one, it'd have to be this one before it hit that one, and then it would bounce it back. Another one would have to be like this, and then a blue range, and it bounce it back. They're almost like basically springs all over the place. Because think about this. People don't consider these things. Okay, look at this book. All right, the same light is hitting that book. Nobody's going to disagree with that. I'm not changing that light between here and coming down to that book. It's the same light. Why is that yellow? Why is this purple? Why is that? Think about it. Just give it a thought. Why is it 2 different colors? Light is nothing more than a spinning particle that bounces off of something. So obviously it's the same particles. There's no difference in the particles. So rule these out. It has to be how hard this surface is. It has to be. When it hits a real hard surface, it bounces back pretty much most of it. When it hits a not hard surface, some of it gets absorbed, and by the time you hit black, it's pretty much absorbing most of that. That's why black things heat up so much. It's really not all that confusing. It's like, they used to call it string theory, but it's actually spring theory. You got like this here, and it's got all kind of magnetism around here in different layers of magnetism. And when this comes in spinning like this, it might bounce off the outer area. If it comes in really fast like this, it might get right up close to the center and bang way back, real hard with blue light. All right, I know this gets a little bit confusing, but it's really not that confusing. I got to be honest with you. If people would just stop and listen and think. It's, but I have some glaring errors in my paper. I have to do that over. I just finally gave up trying to present things in the academic realm. It's just a waste of time. That's why I went to almost exclusively YouTube, and Paul Amatucci wanted to highlight some of my work. But again, and he's throwing in all my work together, even in, like, he's showing all my Mudfossil research in here too. Anyway, this was the first bone of contention with CERN and Fermilab and University of Geneva. They said, you cannot take pictures of photons. I said, yes, we can. We're using CMOS. And they said, no, you can't. CMOS will be destroyed by that. I said, no, it'll be destroyed by what you're doing, not by what we're doing. We're using photons. You guys are using protons. And it's like throwing bombs at it. All right, once again, I mentioned to them that we could use CMOS. They said, no, you can't. I said, yes, you can. But you have to, we use only light, so we're only using one of these particles instead of a ton of them. And I'm showing them the pictures. There was no way to deny it. So then they realized, and I said, you're throwing grenades like this at these CMOS, and yes, you're going to damage the molecular structure, no question. But if you're throwing single particles, totally different situation. So what I ended up doing is integration of a novel radiation hard CMOS sensors. Radiation hard. So they had to do something. I don't know what they did to make it so that these bombs wouldn't break, because they're still using protons. You don't have to use protons. They're looking for the smallest particles there is. Why not start with the smallest particles and see what they do? That's what we do. All right, like I said, I went to the University of Geneva online, and I had nice discussions with them. And this is all about the anomalous magnetic dipole moment. They don't know what's going on with these magnetic dipole moments of these particles. And Feynman, who makes all these diagrams, he's lost too. Now, I also went to Yale online, and I'll show you the course, and I'll show you how it starts out. All right, so don't forget now, this guy Feynman, he does all the equations and all these little squiggly diagrams. Let me show you what they have to say at Yale. Okay, this goes back quite a ways, 12 years ago. But like I said, I went to I do this because I like it. And I took on basically all different universities to what they had to say. I mean, I went to Rice, I went to Johns Hopkins, I went to University of Geneva, and Yale, you come right online here and just take it right online. It's an hour and 13 minutes, and he goes right through it. And I like this guy, Professor Shankar, but it made no sense, and he knows it. That's the key. Listen to this. And again, this is Yale courses. There's no commenting on it. Listen.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do to the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want.
At least he's honest. Okay, my friends, it's as simple as this. This is my claim. My claim is this. Light is a dipole particle. It can be accelerated and obviously slowed down. And that type of particle is the only material that exists. That same particle makes up everything. That means all other matter is made of up and down light particles, and they go spin up or they spin down. It's just because of attraction to the Earth. Nothing else exists. Okay, take a couple of Valium and open your mind. This is all that exists. Is these little tiny magnetic particles, and they're bigger and bigger and bigger. They grow into bigger and bigger and bigger molecules. And that's a whole nother series of investigations, because why would you get big ones that are all attached together, and then you have a hydrogen and helium and little ones that have almost no mass to them? Why is that? There's a lot more to this than just electron flood theory, but you have to start with the true premise of what particles are made of. Nothing can be supported until you understand the nature of the particles that exist. And I've shown them very clearly, because light is the smallest one there is. Now let me compare CERN stuff to what I'm showing. All right, this is what they do, is collide huge particles together. Say this is a proton. For me, this is a proton. All right, so this is just made up of all of these particles. They don't realize that. When they're bundled together as a proton, they're strongly attracted to each other, and they won't fall apart easily. But when they smash them together into another thing, like a neutron, boom, and everything just comes flying out. This is all the kind of debris that they see, and these are the smallest of the debris that they can find. Now remember that? That was the photon. And then they see other little bits of the pieces, which are the red, blue, and the green electron neutrinos, which are all broken away. And the black they don't really see because it doesn't radiate. If it's, for us, we see it because it sits on top of the white and it blocks the white. They're never going to see it because it's just in a big ball of nothingness, and just they see all kind of crazy stuff. But it started out with two big balls like this. Bam! And they just go flying everywhere. Some of them come like this with the X, huge things. This is what destroyed the CMOS. They couldn't do it because it would destroy the CMOS. We're down here. We've got these particles. We're down in the little bitty ones. And then some of them they see like these kind here, and they call them quarks, and they call them hadrons and axions. They got all kinds of names, but it's just debris. It's just nothing more than bits and pieces of debris. It's like you smash two glass balls together, and you got all kinds of stuff. Call it anything you want. And you see, but in here, it's all made of these particles. So you're always going to see the same particles, but you're going to see them in bigger and bigger and smaller masses. That's it. All right, you see, this is Fermilab again, the most successful theory ever, the standard model. It doesn't work at all, but they still are sticking with this. And again, these are the particles that Fermilab again. These are the particles they could see, but they just don't understand them. They know what they do, which is never changes its size. It's called a fixed particle. Fixed, no change. This is the point particle. It gets big, gets small, and it has virtually no mass. That has all the mass. And that's why dark matter, which is this, is most of the matter there is. All right, so don't forget, that's from Fermilab. I didn't make this picture, that's his. We found the particles, yes. This cannot be missed. Those are the two particles, and here they are in light, which is not protons. We're down here. All right, each one of these is a dipole. stuck together. They look just like this. Going through the air, one of them is going to get glowy, and then it's going to flip, and the least one will come in the front. And that's what's called the muon wobble. They spin. Now, you've seen that these are the particles from Fermilab, no question whatsoever. All we're using was light. So, and we can see these in green and blue and red, all the same particle. And when it hit the Venturi, they separated. The black could not get through this slit. It was just too tight. And they recombine out here. And the only reason we can see those blacks is because they're sitting on top of the radiant white, the extremely luminous white. And otherwise we never see them. They don't radiate, they don't absorb, they don't reflect. But they certainly want to be attached to the white. Everywhere you see them, they're digging into the white. And right at that distance, boom, they lock in. And that's why I say, if we had that device I was talking about, something like this, very, very, very simple, with a laser shooting through the Venturi, collecting all, just the white, just the white, just. That's what you want. That's what a generator puts out eventually is it just scrubs the black off the white until it pushes the white in. That's all you want was the white. And it doesn't weigh anything to speak of. That's why your batteries don't get real heavy when you charge them up. And that's all we want. And we've already done it. We just keep it away. Don't let it go through. And you could run that 24 hours a day, 7 days a week. You could have literally hundreds of them, thousands of them in a little shoebox. I don't see why that couldn't be very, very effective to create excess energy. Right here, right there. Just before they come back together is the extreme amount of showers. And they create, well, let me show you. All right, see, they're using protons. They're using things like this, smashing together, getting all kinds of debris. And then they have to decay these hadrons and get high energy neutrinos. And we started with electron and muon neutrinos, which is energy of the neutrinos interacting within this phaser that they developed. The thing is just monstrous. And I still don't think they understand what they did. They just liberated the black particles. But when they do this phaser can go from a few 100 billion electron volts to a few trillion electron volts. And that's an enormous increase in the energy value. And whenever you see luminosity, it's an increase in value, in energy. This is no other way to determine. That's what energy is luminosity. All right, this is the new technologies for the high luminosity LHC, the Large Hadron Collider. They're putting focusing magnets in, yes. They needed to do that. They were just letting things go by and hoping they hit. So they're upgrading to increase the luminosity and increasing the number of collisions. Our collisions are just a staggering number. The aim is to produce 140 collisions each time two particles bundles meet in the center of the Atlas and CMS detectors, as opposed to only 30 at the present. 140 interactions, we do that in a nanosecond. All right, I said I could show you the black pushing the white. Don't forget, there's the black, just like a bowling ball. The white is in front of it. This is a carrier boson. And when I say a carrier boson, they're attached together. The black carries the white. The white has no impact value whatsoever. It just burns. It has no mass. And the black carries it. Now, normally, when the Venturi is set to not allow anything through, the light accelerates and just the white comes through. The black reattaches over here. But you see that huge glow of luminosity? That's just incredible increase in energy. Luminosity is increase in energy. There's no other way to put it. So here it is right here. This is fission when the black separates from the white. And all we have is the white. That's the only thing you want for electricity. So you harvest it here and good to go. The black comes back in out here, so now they come back to being normal particles. But they started out as the muon neutrino and electron neutrino, came back together, or came apart, and the muon went all by itself, what I call a sterile muon, and the electron created showers. There's no messing it. And that's got to be fission, which means it separates, and that's got to be fusion, which means it comes back together. There's no other possibility. Zero. Zero. Here's they were attached together. Alright, check this out. This is that black wave. You see it? Pushing the white wave forward. Before, this was just nothing but white. And ahead of this is a ripple, and this exact same things happen in an atomic bomb blast. This is just incredible, what we have discovered. I got a lot of help from a lot of people. But when this wave comes out, it makes a like that, and then a few seconds later, the real bright stuff shows up and burns something. It doesn't move anything. There's just no impact value from the white. Then the black hits and knocks the house over in a nuclear bomb. I'm going to play it for you in a second. But that's the separation. Now normally we had it where it was just nothing but white, and then they came back together out here. So there's some variety you can do here. You see, normally this here, there's no black whatsoever coming. I don't think. Doesn't look like it to me. And they are the muons and electron neutrinos creating sterile muons and electron showers. There's no other way to look at this. Alright, this makes it pretty simple, all in a row. That's the pulse red laser. No acceleration, it's just pulsing through, exciting the photons, or the electrons that are in the gases, and making them glow a little bit. Now, here's where it accelerates, and we can see there is a particle in here, and that is the particle right there that's coming out of that wave. And it's gaining energy. That's called the neutrino phases. It gets stronger and stronger as it builds up against itself. And here it just explodes. And that, there's no question, it separated the black from the white because of the Venturi. Now, what happened here? It came out this way, and if we were looking into this, that's looking into this right here. Here's the Higgs fields. And then when the whites collect back up with the blacks, they spin like crazy. Now, wait till I show you some of them. Now, this is the particle, is the photon. All right, it gets different neutrino values until it comes up with the full photon, and that's just before it explodes. Now, we also found this, which is extremely interesting. This is an anomaly, and I believe this is a reverse spinning particle interacting with a forward spinning particle, and that particle is stripping the field right off it. So this one's spinning this way, this one's spinning this way. When they interact, it rips the edge right off the field, it looks like to me. That's the only way I can make anything heads or tails of that one. I'm pretty sure this was the particle that it started as a reverse spinner. When these come out, every one of these creates a field, every one of these little spitzes. And normally they spin to the right. They call it the right-hand rule. This one appears to be spinning to the left, like gathering its field into itself or something like that. I don't know. But you can see the other ones are spinning, something's different. And the difference is that when that one hit right up into another one, it stripped part of its field right off it. It looks like to me, that's the only thing I can take out of that. You see this, I call this Higgs on steroids. That's the white spray coming through there, and this is when they accumulate back to the black and they start spinning like crazy. That's what I see. I don't know any other way to see it. All right, just so you understand the neutrino phases. As the light comes in and it's not being pushed back at, it's just sort of going. It has a certain mass to it, which is not much. But then as it starts to stack up against something ahead of it, fields that are in front of it, which is going to get stronger and stronger field as you approach something solid, it starts to change its structure and go sideways. You see here you got two blacks and a white, and here you got, looks like two whites and a black. It just changes a little bit. This is directly into the Venturi, so these turn into the photons. We can see them way out here because they've been accelerated and they're compressing, and we can see them as photons. Normally, I don't know if you'd see those until they hit the Venturi, and then they just be exploded. But because we're accelerating them, we can see them. And this red, the green happens exactly the same. You see the green, exactly the same. These are the neutrino phases, and this is the actual photon phase. That one's getting ready to flip. You see the bottom is glowy, that's the leading edge. It's glowing and it's going to flip, and then the back edge will come out front and start to absorb, and they just keep spinning. They call it the Muon wobble, and that's what keeps them spinning like that. Now you see here the red is pretty easy to work with because it's not so powerful. The green is very, very powerful, and compared to the red, and the blue is just off the charts. So the green is, they're both coming through the same Venturi at the same time. It's a straight up Venturi like this. So one's going up here and one's going down below. The red is below, the green is above, and when they interact with each other's debris field after it comes through, the green just pushes the red right out of the way and goes out and reconcuss his way out here. So extremely strong compared to the red. And the blue is much, much stronger. And that is, the closer they're attached to the nucleus, the higher the energy level will be. So the red is sitting way out here somewhere. The green is down in here somewhere. And the blue is right snug right up against the nucleus. And that's why the blue just comes out like a rocket ship. And the red comes out pretty fast. And the green, the green comes out pretty fast. And the red just sort of bobbles around. And they see the exact same thing at CERN. Let me show you. See, there's a little doodle right from CERN. So now they're taking these and smashing them to bits. Now there's going to be some way down on the inside that are so tight to the core that when they take off, they go blue. And they never come back. They just, they're gone. Now, then you're going to have clouds way out here that are just sort of bumping around a little bit, and they just sort of hang around out the outside. That's the red. But in between the blue and the red, they're not showing green. I don't know why. But there should be all those different colors in between here coming out because there's all these different flavors of energy. They're just different, being pulled away at a different intensity. All right, they're showing some whites and little spritzes of them, which I show too, but and that's what we really want to get down to is the white, and that's the electron showers. All right, you see that? That's the blue, and you could down here you can't even tell there's two particles. You got to get way out to here as it slows down to see that there's two, and the reason is the blue is coming through like this. You see it? And it starts to slow down, and it's slowing down. But you can, and then you'll end up seeing that there's a dipole, two dipoles that make up the particle, the same as all the rest of them. But it is, you can see how extremely sizzling fast it is here, and then it slows down. And light spins. Of that, there is no question. I can show you that very easily. This is what light is. Light doesn't flap like this. Light spins, and it's a particle, and it spins like this. Now sometimes it spins off this way, sometimes it spins and comes straight through the center, sometimes it spins off that way. But this, if you look at this and ask any machinist, they'll say that's the cut of a drill bit. It's spinning. It's a spinning particle. And when they come through the other side, they set up these interference patterns, not because they're flapping one and over and like this. No, absolutely not. They don't want anybody next to them. They create a no man's zone between these layers, and that's what keeps them separated. All right, it's really kind of simple. The light is a spinning disk. Coming down here, and it hits the Venturi. Some of it spins off this way, some spins off that way. Most of it comes dead center through the middle because it's spinning. All right, so don't forget that it's this particle here, spinning like crazy. Hits there, some go that way and come over here, some go under and go off this way. But once they get on the other side, they hate each other. They want to stay away from each other, so they have to keep going. But in order to be happy, they want to keep, you stay your side, I'll stay my side, you stay your side, I'll stay my side. And they keep these interference patterns, they call them. All they are is repulsion patterns. And that, my friends, is a staggering increase in energy. And I cannot for the life of me see any reason we shouldn't be able to take advantage of that and turn that raw electron energy directly into a battery. That's all you want is this. You don't want the black stuff. The black stuff's getting out of the way. It's the perfect solution as far as I can see. But it's going to require a little bit of technical ability, which I don't have the facilities here to do this. It's just so easy, just go ahead and do it. Yeah, that's what I hear all the time. But they'll spend trillions of dollars on these huge colliders all over the world, trillions and trillions of dollars. I've shown you right here more than they can show you at CERN. This is better than they're doing anywhere in the world. If they want to see the smallest particles that exist, there they are. In all the different colors, all the different neutrino flavors. Here it is. All right, just so you know, I sent this a little while ago, a couple of weeks ago, out to virtually all of the top physicists around the world. And I said hello to all. Professor Thomas is, in my opinion, correct about dark photons and dark energy, which to me is also mass. The dark photons, the dark energy, they are basically the mass. Watch how the house burns, but no movement of the fumes, and then the massive dark parts hit and destruction of the house. The white parts have no mass, and I agree with that. That's what Fermilab says. I agree with it. I say at 41 seconds you see the bright photons burn, but not move the fumes even. The fumes don't even change. Then the dark photons destroy the house because they carry the mass. All right, let's just look at that. There it is right here. I sent them all the stuff. All they got to do is look at it. Now, at 41 seconds. All right, let's just look here. There's the house. Boom, watch. I'm going to slow this thing down so you can see it very slow. And you will see that the house doesn't even move. I mean, the fumes don't even move. Check this out. This is atomcentral.com. They're going to explode atomic bomb. First thing you see is every single particle in the atmosphere is glowing like crazy. Now look, this is just burning. It's not even pushing the smoke. All the wires are burning up. The poles are burning up. Everything that's combustible is instantly being evaporated, because takes just an instant. Now will come the black particles, because the first thing that comes out is the white. And I show you another situation that proves it even better. Watch this now. So don't forget, no movement. It's just smoking. And here comes the black. Boom. All right, so let's take another look at something. I want to show you the difference between the white and the black. We just saw the white just burns everything up, and the black pushes everything. So there's a complete difference in their temperature. And one of them doesn't move anything, so it has no weight to speak of that I can figure out. And the other one moves everything, so it has basically all the weight. All right, this is a mind blower. This is absolutely blew my mind. This is coming through the Venturi, the pulses, pushing out here. And what's all this out in front? Why are these in front of the big white wave? I can tell you why, because they are pushed from the magnetic fields. Field. Instantly. That's the key. Instantly, because they are the field effect. The black just pushes. It doesn't. There's no pulsation like this, and I can prove this. Now listen. What I'm going to show you next is an atomic bomb going off, just like here, and we'll hear, and that will be these. And then you'll see the thing come all the way over. The black is coming out, and then boom. So listen, again, the first thing we're going to hear is just like that. And that's the interaction between the actual particles in the air magnetically. They're not going anywhere, they're just glowing. All right, get ready, here we go. All right, listen to this. This is from the nuclear bomb blast. And the first thing we're going to hear is the audio, and we're going to, and that's going to be the magnetic waves coming off. You'll see it explode, and you'll hear it. Listen. You hear that? And now comes a shock wave, and it takes quite a while to get here. but it's propagating across outwards because that's the black matter. You see it? It's coming, and sooner or later, it'll hit up here. Now remember the house I showed you. The house is already basically burnt up. And then all of a sudden the shock wave hits. Here it's coming now. There it is. Same thing we just saw in the house exploding. Alright, so I showed you what I sent to all these physicists. I mean, I sent it to all of them. And I said, I believe that this changes the standard model of these videos that I sent. My model is called Dipole Electron Flood Theory. Claims protons are about 1823 dipoles, neutrons 1824. My experiments are pulse laser light only, so I see the actual particles, not these big debris fields. Proton collisions are simply too many particles to make sense of it. They're just a bunch of debris. I think using electron showers and thin film panels, we might get free energy. Portable, clean, safe, but I don't know. Please let me know your thoughts. Now, I think they're supposed to be there to help us to get free energy, and I didn't see any interest in that whatsoever. None. And I mean, I've been doing this for many years now. It's been close to 10 years. I've been doing my research for years and years and years past that, but really reaching out and saying, look, I have something here that cannot be disputed. This can't be disputed. But you have to look at it, and it's a complete shutdown. And I have found this right across the board in academia. It's very distressing.